And so what happens here is now we're moving from a confidence interval to a hypothesis test. And remember, in a confidence interval, we use a confidence interval when we don't know something. So if we don't know something, we're going to use a confidence interval. All right. Here, it's different. Remember when I showed you the range game on The Price is Right? Linda was trying to guess the price of the trip. She didn't know the price of the trip. They put a range around it. All she had to do was try to guess the true parameter, right? This is different because now I actually know the true parameter. I know what the true parameter is claimed to be. So there is a claim that's going to be made, and in this particular thing, and here's how we started. A hypothesis is used to test the claim of a stated parameter. So we want to test the claim of a stated parameter. And what we do now is we have this stated parameter. So they're going to state something. And you can think of it like, I don't know if y'all follow court cases or not, but if you do, in every court case, the initial claim, the assumed truth, is that you are innocent until proven guilty. That is the assumed truth. And so here's what happens. We start off by saying basically that you are innocent until proven guilty. You are innocent until proven guilty. And that's our initial claim, right? And then basically what happens is this. In a hypothesis test, you become the prosecutor. And you're trying to show evidence that this person is guilty, right? So in hypothesis testing, your evidence is actually going to be our sample data. It's the sample data that's going to be our evidence. And we want to show either that evidence is going to be in favor or against what we call, so this evidence is going to be in favor or against what we call a alternative hypothesis. All right. So the goal here again is to take this initial claim, gather some data about it, and we want to see if the evidence is going to either back it up or go against it. And so the way I introduce this is through the Flint water crisis. And in Flint, Michigan, in 2014, Flint was a part of the Detroit water supply system, right? And they decided that we're spending way too much money being a part of Detroit. Detroit's in Michigan. It's the largest city in Michigan, by the way. So Flint felt like they were spending too much money being a part of that, and they wanted to make it more efficient and basically a cheaper way of supplying their own water. So what they did was they tapped into the Flint River. And when they did that, city officials claimed that the water that they were using was safe to drink. It was safe to drink, basically. But as soon as immediately when they started using it, right, what ended up happening was people noticed that the water often smelled funny. It had a different color to it, and it had a very bad taste to it. So if city officials are telling me that the water is safe to drink, and I'm drinking this water, or if I'm pouring this water, or if I'm smelling this water, I'm not agreeing with what they're saying. So there is an initial claim that's being made. The initial claim here is that the water is safe to drink. And when we talk about that initial claim, we call that the null hypothesis. Let's back up real quick. Let's remember what a parameter is. The parameter is what we call the true value. Our parameters start off with what we call our true value. So what we have is there is some kind of true value to this particular population. In this case, if we talk about Flint, the water is either going to be safe or it's going to be unsafe. One of those has to be true. If we talk about a court case, either the person is innocent or the person is guilty. One of those has to be true, right? And so I like introducing it from the court case, but what I found out when I did this with my virtuals the other day, most of them don't know a whole lot about court. So I'm trying to do it both ways. But in a court case, the initial claim. So in the court case, we call the initial claim the null hypothesis. So this is written as the initial claim. And this claim is always assumed to be true. It's always assumed to be true. And when we write this claim, the null hypothesis is what we call HO. It's called the original hypothesis, or H0, H0, if you want to call it that. But it's called the null hypothesis. And the null is always written as an equality. And what I mean by that is you're going to take some parameter. You take some parameter and you set it equal to something. Well, if you look at a court case, the initial claim is that a person, in a court case, the initial claim is that a person is innocent until proven guilty. So your HO would be that the person is innocent. The person is now innocent. And in the Flint court case, our HO would basically be that the water is safe. So we have safe water. The water is safe to drink. That's our initial claim. And that claim is being made by the city officials here. Here's what happens though. I know from people drinking the water, smelling the water, seeing the water, that it doesn't look safe. I also know that from the evidence I've gathered from a particular suspect that they're not innocent or they don't look innocent. So we developed this competing claim. And the competing claim is what we call HA. It's called HA. It's the alternative hypothesis. And the alternative is written as HA. And again, this is the one that we need to show evidence. We're going to show our evidence either in favor or against. Well, evidence is either going to be in favor or you'll have a lack of evidence, which goes against the alternative. The alternative itself, HA, will always be written as a parameter, and it can be one of three things. So it'll be a parameter here. Come back up here to HO. HO has to be a parameter that's always written as equal. HA, the alternative, will always be written as either the parameter is less than, greater than, or not equal to for this particular symbol. And it depends on what the alternative is that you're checking. So we come back to the Flint court case. Here's what we have, or the Flint case, real quick. In the Flint case, it says, immediately residents began noticing different problems with the new water supply. The color, taste, and odor of the new water were all things residents stated to the city officials. Also, people were getting sick and some even died. As a show of confidence, the mayor went on TV and even drunk freshly poured tap water from the city's water supply. Let's test the residents' claim using a hypothesis test. We will assume that the water is safe when it has levels of lead less than 10%. So they're telling me it's safe. I'm defining safe right now as a lead level that is less than 10%. So if they're telling me it's safe, the null hypothesis that I'm going to create, HO, for this particular parameter, because it is a percentage, the parameter we're going to talk about is the proportion. The proportion. So the proportion of lead in the water is less than 10%. So when P is, and we write the parameter, we write the HO always equal to as an equality. So we always say this is equal to 0.1. What this really means though is that for our particular parameter P, and in this case that's the proportion of lead in the proportion of lead levels in the water, is equal to 10. It can be equal to, it's safe if it's equal to 10% or anything that is less. As citizens that drink this water though, we say that it's not safe. We're saying that this is not safe water. So what we're really saying is that we're testing this against the alternative. Well, it's not safe when the lead levels are greater than 0.1. And I want you to notice that even though I said equal, the equal here takes into account the fact that it is equal to 0.10, but it also takes into account that it's less than 0.1. Because anything less than 0.1 will also be safe. And that's why we always write this as an equal sign. Because whatever alternative we use right here, we're going to assume that the other one belongs to this one as well. So if I use greater than here, I'm going to assume that this one is equal or less than. But we always just put equal. So here are here's your Flint hypothesis. I should have wrote that there. No, folks. Here are the Flint hypothesis. And what we're going to do now is we're going to try to test this. We're going to go through and try to test this. And see if the water is actually safe. And in court, let's go back to the court case real quick. In court, your alternative hypothesis, well, here, you're innocent. or the alternative here is that you are, we write it as not innocent. And we do it like that for a couple reasons. Here's what happens. Remember what I said up here when I talked about the true value, the parameter? The true value does not change. This value up here will not change. When I write the hypothesis, I'm always writing the parameter P and P here. They're the exact same value. They're the exact same parameters. And as a matter of fact, this value right here, this true value, is not going to change. The initial claim is not going to change. What changes is going to be the sign in the middle. This one's always written as equal to. HO is always equal to. HA is dependent upon the problem that we're trying to look at in our sample data. So when I look at something like this, if I write the court analogy, then you are innocent. That's the initial claim. The alternative is that you are, I'm changing that innocent to not innocent. We know by default if you're not innocent, that means you are really guilty. But we always use that terminology as innocent or not innocent. All right? Innocent or not innocent. Or you keep the parameter the same, you just change your signs. So here's how this works then. Here's what we're doing now. What we're going to do is we're going to gather data. And the alternative directions are based on the signs. And they're based on what your sample data is actually saying. So if they're telling me that lead levels are 10%, and I look at a whole bunch of homes and I measure their lead levels and they're 8%, then now I believe that most of my lead levels are falling out here. And this is what we call a less than or a left-tailed test. So we call it a less than or a left-tailed test. And this is written as HA is, we're talking about P, the proportion, P is less than. And what it's saying is that anything that falls on this side, is basically a safe value. Anything out here is what we call a safe value. And what that means, if it's safe, that means that the P that they're giving us for HO is plausible. Notice I use the word plausible there, and I'm not using the word true. And we'll get to more of that in a second, but HO is plausible, means it's believable. However, what this is also saying that now, if it falls in the green, it's plausible. If it falls in the red, then that means that HA is more plausible. I'm not using the word true, I'm using the word plausible, believable. Because again, we don't know that we technically don't know the true parameter. We've been given a claim for it, and it could be true or it could be false, but based on our sample, we're going to base everything off the sample. And so when we do this, we can do it for a left tail or we can do it for a right tail. And in a right tail, here's what happens. In a right tail, most of your sample values are going to be, your sample, when you gather your sample, is going to be bigger than what's stated. So if we look at a whole bunch of homes in Flint again, and instead of getting a 0.1, we get a 0.15. Well, now we think that what you're telling me about HO being safe in this region is not true, right? And I'm thinking that most of my values are going to be bigger than this 0.1. And remember, your 0.1 is the mean, so it's going to fall at the middle of the curve here. So the value is bigger than 0.1. 0.15 falls somewhere out here. So you're falling in what we call the rejection region. And both these areas where we think HA is more plausible, this is called the rejection region. It's called the rejection region. Because what we're going to do is we're going to reject the claim that you're stating to me. And in a greater than test, in the right tail test, we say HA is P is greater than some value. Right? P is greater than some value. And then the last thing is, here's what happens. If we don't know the direction, right? Then what we do is called a two-tailed test. If we just think that it's different. The first two are what we call directional tests. Right? The first two we call directional tests. And in directional tests, in the wording, they're going to tell us that the sample either was more than or less than something. In a two-tailed, or what we call a non-directional test, They just tell us that it's different. We don't know if it's greater than, we don't know if it's less than, we just know that it's different. All right? And so in this particular case, when we want to say that something is different, we have to check both tails. So you can, if you're telling me that P is 0.1 and I'm getting sample values of 0.8, 0.08, or sample values of 0.15, I don't know which one is actually falling into. I just know that what you're telling me is not true. When we do this, our HA is written as P is not equal to something. So there are three alternatives that we're going to create, and they're based off the wording of the problem. And I'll show you how we write alternatives in these examples right here. Right? I'll show you how to write them in these examples right here. So in the first one it says, a large poll showed that 42% of adults approved of their nation's prime minister. Sarah wants to test if it is now lower. So she takes a random sample of 1,000 adults in that nation and finds that 390, or 39% of those sampled, approve of their prime minister. If I want to create a hypothesis here, here's what I do first. I need to identify what is the parameter. And we've been identifying parameters a lot. We do it in confidence intervals. We did it when we did panic, when we said the P. What does P equal? Well, here, my P is equal to the number of adults, or the proportion of adults that approve of their nation's prime minister. This is P. This is what P represents. P is the proportion, the true proportion of adults that approve of their nation's prime minister. The large poll showed that it was 42%. So the claim being made right now, the initial claim, HO, is that P is equal to 0.42. Claim being made is that P is equal to 0.42. Sarah takes a sample. She takes a sample of 1,000 adults and finds 390 of them approved, which is only 39%. So she's already thinking, if you ask her what she's thinking that the sample is less than, or the actual value is less than what's being stated. And that's what she's going to test based off of her sample. So we build our test based off the sample and the wording in the problem. And it says that Sarah wants to test if it is now lower. So if she wants to test if it is now lower, our alternative here, the alternative is that P is less than 0.42. That's what Sarah believes and what Sarah wants to show evidence in favor of. Notice here, though, when I wrote this, parameter P does not change. Both of these represent the true proportion of adults who approve of the nation's prime minister. The first one says that value is equal to 0.42. The second one says that value is less than 0.42. When I wrote this, though, I didn't change this number right here to 0.39. We don't change it to the sample. We leave it as the parameter, the population value. And that is key when you write these, so be careful with that. Make sure you're always writing a parameter here. Make sure that this is always equal to here. Make sure that these numbers are always the same back here. The only thing you're going to change is the sign in the middle. So look at the next one. It says, a business knows that 30% of its customers are less than 25 years old. The business wants to increase this percentage. So they create a marketing campaign that targets this age group. They plan on taking a sample of customers after the marketing campaign is complete to test if the proportion of customers in that age group has significantly increased. We want to test to see if the proportion has significantly increased. We're doing the marketing campaign because they want to increase this percentage. Because of all of these words that say increase is going to tell me I need to do a greater than test. They know from their previous thing that the value right now, the parameter, and the parameter in this case is the proportion of customers that are the less than 25 years old. This right here is your P. The true proportion of customers that are less than 25 years old. So when I write this HO, P is equal to, well, they know right now it's 30%. They wanted to increase after the marketing campaign. So HA, if they wanted to increase, we're going to test. We want to test for evidence that it does increase. This is P is greater than 0.3. Again, notice parameter is not changing. Value for the parameter is not changing. The only thing changing is the sign in the middle. And the sign in the middle, the sign down here, this first one's always equal to. This one is based on the sample and what you're trying to show evidence in favor of. A manufacturer knows that 2% of its microchips are produced with a certain defect. They decide to change their process to make it more efficient, and they want to test if the new process has the same defect rate or not. So they want it to be more efficient. But one of two things can happen. It can be more efficient, or it can not be more efficient. So what they're really saying is that we don't know if it's more efficient or not. We just want to see if it's different than the current 2% that they're stating. So in this particular problem, we know that the parameter is the proportion of microchips that are produced with a certain defect. Here's your P. The true proportion of parameter, the true proportion of microchips that are produced with a certain defect. They want to make it more efficient. And again, we don't know if more efficient means that they're going to have, we know more efficient wants to be smaller, but we don't know if that's actually going to happen. We just want to know if it's different than 0.02. So your null, HO, always equal. P is equal to 0.02, the initial claim. HA. P is, because I don't know the direction here, I'm going to go not equal to 0.02. And again, remember, on this particular problem, we're not changing P. The parameter is set. It's the true parameter. It's always equal to an HO. The initial claim is always equal to something. HA is not equal to something. Right? So the first part of any hypothesis test is generating the hypothesis. Right? The first part of any hypothesis test is generating your hypothesis. And once we have our hypothesis now, here's the goal. Once you know what your hypotheses are, you want to show evidence that what you believe is plausible. And the way we show evidence is like this. Here's how this works. The actual logic behind the hypothesis test works like this. They always start by assuming the null, your null hypothesis, which is HO. They always assume that the null, HO, is true. When you go to court, we assume that you are innocent until proven guilty. Flint, Michigan says that the water is safe to drink. We're going to assume that that is true. And then we're going to calculate our evidence based on how unlikely it is to gather a sample if in fact the null is really true. So in a court case, for instance, here's what it really means. We have a person that is on trial for murder, right? And this particular person is considered innocent until proven guilty. And here's the evidence that we actually have. The evidence says that this person was a African American male, right? They're an African American male that is 5 foot, let's go 5'11". They wear glasses. They had on a hoodie. We'll stop there for right now. So if I ask you that question, here's what I want to know. How unlikely is it to find in our population an African American male that is 5'11", who wears glasses and has on a hoodie? Is that highly unlikely, or is it highly likely to happen? Well, those things are all circumstantial. And because they're all circumstantial, they're probably very likely to occur. And when we say very likely to occur, we're talking about very likely to occur by chance. But here's more stuff. What if I tell you that this is an African American male who is 5'11", with glasses, that wore a hoodie, and we know that the suspect drives a pink Corvette? Well, that last piece of information, the pink Corvette, if I pick up a person, an African American male that is 5'11", who wears glasses, has on a hoodie, and is driving a pink Corvette, that last piece of information makes it very unlikely that this person is part of the sample by chance. It makes it highly unlikely that chance alone is why I found this person. That's what we're really saying. And what it really is saying, that systematically, or in this particular case, this is the actual murder suspect. This is the actual murder person, the person who did the murder. This is the actual person who did that particular crime. We have enough evidence to say that now. Because of the pink Corvette was the part that said, this is too much. So in the court case, what you're really saying stuff like is, how unlikely is it I find the murder weapon at this person's home if in fact they really did commit the murder? They didn't commit the murder. Well, you can find the murder suspect. You can find the murder weapon at a suspect's home if in fact they didn't commit the murder. It may be somebody else that dropped it off at their home. It may be something like that. So there's circumstantial. But when you start to add different pieces of information, it starts to be a thing that this doesn't happen by chance anymore. For instance, in the Flint court case, how unlikely is it that people are getting sick and dying from the water if in fact the lead levels are really safe? Well, people can die and get sick from the water, but again, if the lead levels are really safe, how likely or unlikely is it that people are going to do this? That's what we're asking now, right? And now what happens is then when I do this is I'm going to gather this data and I'm going to find this thing that we call the test statistic. And the test statistic itself is a z-score. It's just a z-score. And we may or may not remember what a z-score is, but remember z-scores measure they measure the number of standard deviations. The number of standard deviations you are away from the mean. And what happens is this, every z-score is on a normal curve. They're all on normal curves like this. And all their means have a mean of 0 and a standard deviation of 1. And remember, there are 6 standard deviations under every curve, under every normal curve. Right? And so in a z-score, here's what happens. We're going to calculate the z-score value. And to calculate a z-score, z for this is equal to, we're going to use the proportion p minus p hat over the square root of, I wrote that backwards. It's actually p hat minus p. The sample minus the population. So it's p hat minus p over square root of p q divided by n. That's the z-score we're going to use here. And the z-score is going to put us on this curve somewhere. And what ends up happening is when you do this on this curve, right, you're going to be, the closer you are to values of 0, the closer you are to values of 0, the more likely something is to occur. The further you start to move away from 0, though, the more standard deviations start to move away from 0, the more unlikely it is to occur by chance. So here's an example of what I mean. If we look at the Flint, Michigan case, here's what they did. In that particular sample, what they did, they grabbed a sample of 252 homes, and they were randomly sampled from the population of Flint. In this sample, 42 of those homes had unsafe lead levels. What is the test statistic for this sample? So in order to calculate the test statistic, I first need to find p hat. Well, there were, how many homes were sampled? 42. Out of how many total homes are there? I'm sorry, there were 252 homes that were sampled. 42 of them had unsafe lead levels. So p hat is equal to 0.42 divided, I'm sorry, not 0.42, just 42. 42 divided by 252. And we want to give that a decimal. The decimal I'm getting for that is 0.167. So if that's 0.167, let's talk about that. We know that the safe level, percentage or the percentage of homes that should be safe, P is equal to 0.1. That was written in our null. Here I found 16.7%. This is already telling me that something's not right. I shouldn't be able to grab a sample that has such a large difference between these two values, by the way. If I want to find out how big of a difference that is, here's how I calculate that then. The actual difference is, we use the z-score. Z is equal to the statistic, which in this case is p hat, 0.167, minus the parameter, which is 0.10. We divide that by the square root of, you've seen P cubed divided by N before, but you've seen it in confidence intervals. In confidence intervals, we saw it as P hat Q hat. We no longer call it P hat Q hat. We used it in confidence intervals with P hat Q hat because we had to draw everything from the sample. Here we actually have the population values, and anytime you're given population values, you always want to use them. So in hypothesis tests, we always use the parameter values. So here we're going to do 0.1, that's P, Q, 0.9. Remember, I get that 0.9 by doing 1 minus 0.1. So that's 0.9. I'm going to divide that by the sample size, which in this case is 252. I'm going to calculate a z-score for that. So to calculate that z-score, I'm going to do 0.167 minus 0.1 is this. Divide that by the square root of 0.1 times 0.9 divided by 252. Here's what I get. My z-score here then is equal to 3.545. 3.545. I am 3.545 standard deviations above the mean. Now, if we go back to our curve then, 3.545 puts me way out here. This is a z-score of 3.545. And what that means then now is this. First off, I want to know, is this value a typical value or is it not typical? Typical values will fall around 0. Because typical here means, are they close to the mean? Right? But I see that this value falls way out here, more than 3 standard deviations away from the mean. So this is highly, this is a very atypical value for what we're looking at. And I want to know now, how atypical is it? Well, every z-score now has a probability associated with it. And when we talk about that probability, we talk about this thing that we call a p-value. And the p-value tells us how unlikely something is to occur by chance. So a p-value gives the probability of obtaining a sample as extreme, or even more extreme, if in fact your null hypothesis is true. So here's what I'm saying now. I'm on a normal curve. The null on this is 0. I'm at way out here at 3.545. Right? I'm at that value way out there. And remember, this would be on a, if we did it with the regular numbers, we'd have a mean of 0.1 sitting here. That's what the hypothesized value was of the population. We got a sample value of, this is 0.167 sitting way out here. And here's what this is saying now. The chances of getting a value as extreme as 3.545 sits here, or even more extreme, would be something that goes to the right of here. That's what we call our p-value. This right here is the p-value. And I can look at this and tell you that this p-value is very small. It's sitting in the tail out here. And what it's really saying is that if in fact the water is really safe, that is the null here for Flint, if in fact the water is really safe, how unlikely is it for me to get a sample statistic that is 3.545 standard deviations away from the mean? It's highly unlikely for that to occur by chance. Highly unlikely. That's what this is saying. It's so small. Right? So here's what you're asking yourself in a court case. How unlikely is it that I find the murder weapon at the person's home if in fact they really didn't commit the murder? So if in fact you're really innocent, Should I find the murder weapon at your house? Is that likely? It could be, but it starts to leave more suspicion and guilt. Likewise, how unlikely is it that people are getting sick and dying from the water if, in fact, the lead levels are really safe? So, if my lead levels are really safe, how unlikely am I going to have people dying and getting sick from this water? It should be highly unlikely. It should be this right here. This one right here is what we call plausible. This is pretty plausible. It's not good news, but it's plausible. You can find the murder weapon at somebody's home and they didn't commit the crime. This though right here is not plausible. This is highly unlikely. If you're drinking that water, and a lot of people are drinking that water, and a lot of people are dying from it or getting sick from it, chances are the water's probably not safe. And so when we calculate the p-value here, then the p-value is just an area on the normal curve. This is just area on the normal curve. If I want to calculate the p-value, I'm going to use the normal CDF function. So to calculate the p-value, I use normal CDF. I use normal CDF. In this particular case, I look here, my lower bound is sitting here at 3.545. My upper bound, remember when I calculate my upper bound, it goes all the way to infinity out here, so we're going to do 99999. My mean is 0, standard deviation is 1. I can calculate that in my calculator. I know how to calculate this in my calculator. This is menu 652. Menu 652. Menu 652 in your calculator. If you calculate it using menu 652, I get a very small value. That is e to the, I think when I did it, I got this right here. Here's how we write it, by the way. You write it as a probability statement. The statement says this. It's the probability of getting a z-score. Look at this curve getting a z-score that is greater than 3.545. I think when I calculate, I got 0.0002, like this. So you get a 0.0002 chance of actually getting this particular value by chance. And this, what we call a probability statement, and this probability statement says that I'm looking at a z-value. I'm looking at a z-value that's greater than, because that means that you're as extreme or more extreme than the actual value. That only occurs 0.0002% of the chance. 0.002% of the time. And so now what happens is we can take this and we can make a decision. And we make our decision based on this thing in a significance test called the level of significance. The level of significance is the Greek letter alpha. This is the Greek letter alpha, it's lowercase alpha. And this level of significance is a cutoff value for what we think things are too unlikely. Or in this case, what is plausible versus not plausible. What's plausible versus not plausible? And what you're asking yourself is, what percentage of the people have to get sick or die before we no longer accept the null? In a court case, what piece of information do I have to see before I no longer think the person is innocent? That's what happens. And from there, we do this thing that we call a rejection rule now. We can develop what we call our rejection rules. And either one of two things are going to happen. You're going to reject, or you're going to what we call fail to reject. If you think of a court case, the null hypothesis that the person is innocent. Here's what happens. When you reject a person's innocence, you are now saying that they are guilty. So when you reject a person's innocence, you are now saying a person is guilty. In order for that to happen, things have to be so unlikely to happen by chance. There has to be there has to be a small probability that things can happen by chance for this to occur. So this rejection rule is called the low rule. We're going to call it the low rule. And in the low rule, if the alpha value, if the p-value, if your p-value is less than your alpha value, you're going to reject HO. You're going to reject HO. So when we reject we're going to reject the null hypothesis. And what this means is you're rejecting, if you think of a court case, you're rejecting somebody's innocence. If I reject their innocence, what I'm really saying is that when we reject the null, what we're really saying is that there is enough evidence. There is enough evidence to support their guilt. I don't want to say guilt. To support HA. That's what I'm going to say. So if I reject your innocence, what I'm saying is I have enough evidence to support your guilt. And this is how we work this. In a court case like that, but even in the Flint case, what you're saying is if I reject that the water is safe, I can only reject that claim because there's enough evidence to support that it is unsafe. And we do that when we have a small p-value or a value that is lower than alpha. This other one is called the higher rule. And the higher rule, or high, if you want to call it that, is when the p-value is greater than alpha. And here when you reject your null, here's what happens. Or this is what we call the fail to reject rule. We're going to fail to reject the null. Or in a court case, you're going to fail to reject that the person is innocent. What does it mean if I fail to reject you are innocent? Think about that. If I reject that you're innocent, that means you're guilty. If I'm failing to reject that you are innocent, that means that you are still innocent. You are still innocent. And my goal is to show that you are not innocent, by the way. That's my goal. I want to show that you're not innocent. But I have failed to reject that you are innocent. What that really means is I'm saying that you are still innocent. Why are you still innocent? Well, I'm saying that because there is not enough evidence here. There is not enough evidence to support HA. In the case of a court case, that would be there is not enough evidence to support your guilt. In the case of Flint, that would be that there is not enough evidence to support that the water is unsafe. But this thing that we're talking about at the very end is called our conclusion. And when we make the conclusion, it's made with respect to two different things. The first thing is whether you're going to reject or if you fail to reject. And the term fail to reject is kind of difficult to understand when you first learn it, but it makes a lot of sense if you apply it to real life. Because what's happening is this: when you fail to reject something, you're not accepting it. And what I mean by that is if you say, well, if I fail to reject somebody's innocence, that means they're still innocent. That means I've accepted their innocence. I'm not accepting their innocence. For one, their innocence was not the thing that was put on trial. Right? And what I mean by that is you are initially assumed innocent to begin with. Which is why when you get a lawyer, they tell you don't talk. Because all you can do is incriminate yourself. Right? But the other thing is, if we go through this entire test and we fail to reject that a person is innocent, which means they're still innocent, well, there are plenty of times when a person has been found innocent, but they've actually committed the crime. So I don't accept your innocence. I just fail to reject it. I don't have enough evidence to support what I'm trying to show right now. But we always start by saying, with respect to the null hypothesis, do I reject the null or do I fail to reject the null? That is the first part in the conclusion. Do I reject? I only reject when the p-value is less than alpha. Or do I fail to reject? I fail to reject when the p-value is greater than alpha. And once I decide those things, here's what's going to happen. Why have I rejected your innocence? Well, I've rejected your innocence because there is enough evidence to support your guilt. In this case, guilt is HA, the not innocent. Or in Flint, I've rejected that the water is safe because there's enough evidence to show that the water was unsafe. If I fail to reject, why am I failing to reject your innocence? Why am I not taking your innocence away from you? I can't take your innocence away because there is not enough evidence to support that you are not innocent. Or in the case of Flint, there's not enough evidence to support that the water is unsafe. And next time I see y'all, we'll actually talk about doing an actual hypothesis test. But right now, this is the basic logic behind an entire hypothesis test.